Hi everyone. So today we're going to be looking at chapter 22, electric fields, lesson 1. It's about point and spherical charges as well as Coulombs law that we're going to look at too. We will start first with what electric fields are, how to model uniformly charged spheres as a point charge at its center, electric field lines to show electric fields, and what electric field strength is, the definition, and how to calculate it. So we already have seen gravitational fields. Now, electric fields and gravitational fields share a lot in common between them, which we will look at the end of this lesson. And just as a very quick and brief reminder of fields. So we already saw gravitational fields. We will talk about electric fields. And in the next chapter, we'll talk about magnetic fields. Now, all this, what we mean about a field is just simply the area or a region where a force will be experienced on an object at a distance. So it's a region where a force can be exerted on an object at a distance. So they're all non-contact forces, so the objects don't have to be in contact for them to experience an attractive or repulsive force, depending on what field we're talking about. Also, the fact that we talk about different types of fields. So for gravitational field, is a mass that causes it. So the actual field or property is caused due to mass. For an electric field, it's a charge that causes it. We know there's two types of charges, positive and negative charges. And in terms of the smallest parts that make up objects, is protons and electrons. We will see more when it comes to particle physics that protons can actually be broken into something smaller, but cannot exist on their own. So we're going to talk about it when we come across that later on. And then we also have magnetic fields, which are caused by magnets or magnetic materials, or even charges moving. But we will come up to this one later on in the next chapter that we'll look at through with you. So let's go and start. So we kind of talked about fields. Always remember, it's a region where a force can be experienced on an object at a distance. In the case of gravitational fields, it's masses, and the field is caused by mass. In the case of electric fields, a charge causes the electric field, and another charge experiences a force due to it. In terms of magnetic, we'll come across that later on. So an electric field is a region around an electric charge where another charged body will experience a force. It is caused by an electric charge itself, okay? So any charge, electrically charged body. But unlike the gravitational field that we saw, the electric field can be attractive or repulsive in nature. So we will have electric field lines to represent electric fields that are towards or away from the charged source. So electric fields, once again, just to remind you, are caused by electric charges or by charged objects. Now, this is a quick reminder I'm going to give you through from your GCSEs. We saw that if we wrap two insulators together, through the action of friction, we are transferring electrons from one object to the other. This means one object has less electrons, which means if it's lost electrons, that means it's positively charged, and the other object has gained electrons, and that means it's negatively charged. So I can easily create charged objects by rubbing two insulators together. Electrons get transferred from one to the other. Just again, a quick reminder, always you have a nucleus that's got positive and neutral subatomic particles. So you have the protons and neutrons, and then around it you have electrons. It's always easier for an object to lose electrons than to lose its protons, hence why always electrons get transferred. Protons and neutrons are held together strongly by the strong nuclear force, which we'll come up to in another chapter. I think it's chapter on nuclear physics, but we will come across it either way. These were just quick reminders from GCSE, as well as seeing charged objects and their electric field around them. Also, we have two charges here. So we have the positive charge and the negative charge. If we assume that these are point charges, meaning that all the charge is concentrated at a very small area, we can draw the electric field lines around them. And as you can see, the positive and negative charge have the direction of the electric field in opposing directions. And we will explain that as soon as we look at the definition of electric field strength, why the directions are different and why the electric field lines are away from it. But similarly to gravitational fields, around a point charge, you have a radial electric field, meaning it spans across the whole area around it in a radial field, a circular field. Okay, so before I continue on, we need to know what electric field is, its definition, its equation, and obviously their units. Now, electric field strength is defined as the force experienced per unit positive charge at that point in the field. So the most important part here is not to forget this positive part. And I will explain as well what that is. So once again, if you want to remember what electric field strength is defined as, is the force experienced, and especially when you're already given the equation, is the force experienced. So electric field strength is given by this symbol. Which is the force experienced per unit positive charge at that point in the field. Which makes this a vector quantity because it will be different for positive charge and different for a negative charge. This is the force and this is charge. So we know the units for force are newtons, the units for charge are coulombs, which means that the electric field strength is newtons per coulomb as an SI unit. Okay, so let's do this example very quickly before we move on to explain the direction of the electric field. So you have an alpha particle that has this much charge, and it is placed at a point in an electric field where it will experience an electric field of strength, this much. Calculate the force of the alpha particle will experience at that point in the field. So we place an alpha particle, which is 2 protons, 2 neutrons, in an electric field. Then what would be the force it will experience? That's all it's asking us. So we're given the charge, we're given the electric field strength at that point in the field. So we need to calculate the force that's acting on it. So we have E is equal to F over Q. We rearrange for F. So it's the electric field strength times the charge, which gives us 3.2 times 10 to the minus 19 for the charge times 4,800 newtons per coulomb for electric field strength, and we should get 1.5 times 10 to the minus 15 newtons for the force that it will experience while it's at that point. So this is a quite straightforward question. Now, when it comes to drawing electric field patterns, there's one point that's quite important in this topic. And this is the first point here. So it says the direction of the field lines represents the direction of the field. It always shows the direction a positive charge will move in the field. So for a positive point charge, if I placed a positive charge within the field, so if I placed another positive charge here, it will be repelled. We know that positive and positive repel each other. So if I have the electric field around the positive charge, it should be showing the direction that the positive charge will move if I placed it in that field. And in this case, we know that positive and positive repel, so it should be away from it. So you can see that the electric field direction always goes away from positive and towards negative, because if I place the positive charge near a negative charge, it will attract to it. So we know positive and negative attract, and negative charges repel. These are a simple reminder from your GCSEs as well. So now the other parts are quite similar to gravitational field patterns. The electric field lines should always be at right angles to the surface of a conductor, and you can see that at each point around a charged sphere or a point charge, it is at 90 degrees to the surface. They should be equally spaced for parallel electric field lines and uniform electric fields. What you can see here. So if we have a uniform electric field between two oppositely charged plates, like you see here, so you see the power supply is connected, the positive side of the power supply is connected to this plate here, which gives it an overall positive charge. The other plate is connected to the negative terminal, which gives it a negative side overall. So what you have between positive and negative parallel plates is a uniform electric field, meaning the electric field strength is the same here as it is here, as it is here, and so on. Quite similar to gravitational field strength at the surface of the Earth, basically. It's uniform, the lines need to be equally spaced between them, and only at the sides of the plates it kind of curves a little bit, because it stops having that uniform field there. So also the next point that applies to every field as well, if the electric field lines are close to each other, then you have a stronger electric field. So if I wanted to compare the electric field strengths of 2 point charges with a drawing, it should be like this. So for example, and obviously your arrows everywhere. So this field is stronger than this field here. So that's how we represent them simply. And you can also see that we also have the field between positively and negatively charged spheres. We always treat them as the same way that we treated gravitational point masses. So the gravitational field lines around a point mass. We always treat charged spheres as that they have point charges in their center. So all the charge is concentrated at their center, and hence we always look at the distance from the center as well. So this is the basic things regarding electric field patterns. Now that we know about the direction of electric field, this is another example. This one says you have a negatively charged dust particle, that moves from left to right, so it moves in this direction, in a uniform electric field. It has a charge of this much. It also experiences a constant force of this much. Calculate the electric field strength, so I need to find E, and state the direction of the electric field. So we know that E is equal to F over Q. Simply put the numbers in. Whatever we get, the answer will be the electric field strength. And to state the direction of the electric field, well, if the negatively charged dust particle moves from left to right, that means that the electric field is from right to left in the direction that a positive charge should move if it was placed in that direction. So that means that it's attracted to a positive charge itself. So going back to the learning objectives, we have looked at the electric fields that are caused due to charges. We also modeled the uniformly charged sphere as a point charge at the center. Talked about the electric field lines to mark electric fields and their rules, and what electric field strength is and how to calculate it. Now we'll have a look at Coulombs law and how it can apply to radial fields as well. So we'll look at Coulombs law, so how we can calculate the force between 2 point charges, what electric field strength can be calculated as around a point charge, and then we're going to compare the similarities and differences between gravitational and electric fields for a point charge, and the concept of electric fields as being one of the number of forms of fields giving rise to a force. So we already kind of talked about this. It's just about understanding it and putting it into context. So let's start with Coulombs law. Now, Coulomb said that at any 2 point charges exert an electrostatic force on each other that is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. So if I were to write this down as an expression to begin with, that means the electrostatic force is directly proportional to the product of the charges. So Q standing for charge 1 and Q lowercase standing for charge 2, and inversely proportional to the square of the separation between them. So in other words, this is the expression, this is Coulomb's law when you're describing Coulomb's law. So the force is directly proportional to the product of the charges, inversely proportional to the square of the distance between them. But that means that there's always a constant when we have a proportionality relationship, which comes up to this equation. So this is us deriving the expression of the electrostatic force experienced by point charges, because we said already that if you have uniform electric field, you don't use point charges, you have plates, and the field will be the same everywhere. So in that case, we only need to use this equation for uniform electric field forces, and this is for radial, similar to what we have seen in gravitational fields. Now, can we derive an expression for the electric field strength from this? Of course we can. We already know that E is equal to F over Q. If I now substitute in this equation the force experienced by radial, by point charges, then that would leave me with KQ over R squared divided by Q. In this case, it will be lowercase q, because of the charge that experiences the field due to the bigger charge. So it leaves us with KQ over R squared. So I have mentioned that K is the constant of proportionality, but in this case, K has its own very specific value. So K is equal to 1 over 4 pi epsilon naught. It's not an E, that's an epsilon, a lowercase Greek letter epsilon, and naught. We will come to what that means, but later on in the chapter, but I will just simply state what this one is. This is the permittivity of free space. We will come across this again later on, like I said. I won't spend too much time going into it now. So I can rewrite my expressions. So how we have our expressions written here as kq1 q2 over r squared. We can rewrite it in these terms, or in this term. For the force, that will mean that the electric field strength can also be rewritten as q over 4 pi epsilon naught r squared. For calculating the electric field strength around a point charge, or something that we model, so a spherical charge object that we model as point charge. So any charge objects like a proton or an electron exert the force on each other. The charge, the point, they can consider as point charges because they're so tiny, as well, and as well as big objects. So if I had a big sphere with charge that's charged, I can also model it as a point charge and use these equations, and they will be fine as long as I take the distance from their centers to be r. So from the separation distance should be from the center. So r squared should be the distance from the center of each spherical object. Permittivity of free space is also given to you in the formula booklet as one of the constants that you need to know. That's about it in terms of Coulombs law. Also, just to I'll make it very clear what units we're using for each of the quantities. So for charges is coulombs, and for the distance, the separation between them should be in meters, and then epsilon naught, which is the permittivity of free space, is coulomb per newton per meter squared. Also, another part that we do need to consider is whether charge Q1 and Q2 are positive or negative. In the case of having a positive and a negative charge, what you will have is, for example, minus Q times plus Q over 4 pi epsilon naught r squared. That will give you a negative expression, which yourselves already know that positive and negative attract. So a negative value of force will mean that the force is attractive. If it's two of the same charges, so two positive or two negative charges, F will be positive, which means the force is repulsive. So that's another part that you should definitely gather from this equation too. And as a reminder as well, according to Newton's third law, if charge Q2 experiences a force F due to charge Q1, then charge Q1 will also experience the same force in opposite direction due to force Q2. So another thing I wanted to mention here before I move on is once again, how do we deal with the resultant force acting on a charge if it's got more than one charge around it causing forces on it. So for example, if I had a positive charge, another positive charge, and then I placed another positive charge in between them. So let's name this Q1, Q2, and Q3. Now, if I wanted to know the overall force, the resultant force acting, electrostatic force acting on charge Q due to charge Q1 and Q3, I will have to calculate the resultant force as the vector sum of all the forces acting on it. So one of the forces will be the repulsive force from charge Q1, because it's obviously repelling it, so it will be in this direction. And also, since positive and positive repel on this side, Q3 will also repel charge Q2. So if I wanted to know the resultant force of these two forces, it will be F1, if I take this to be the positive direction, plus minus F3, because it's in the opposite direction. So what if they were not in the same line of action? What if it was in a 2-dimension and I had to figure out the force as well? Well, once again, a simple way of looking at it is that if these two are in the same direction, and I wanted to know the resultant force acting on charge Q3, for example, I know that charge Q1 will be attracting it. So I can draw an attractive force here, which is F1, so the force caused by charge Q1. But then positive and positive repel, so Q2 will be repelling Q3. If I take the line of action, it will be in this direction. So what I have is the force of charge Q2 acting on Q3 in that direction. Hence, I will have to take into account the angle to be able to calculate, or even its components, depending on what the question is asking or gives me. Also, the same thing can be done for electric field strength. Since electric field strength is a vector quantity, we can always calculate the electric field strength at a point away from a charge, and then take the sum of the vectors of electric field strength at that point by indicating which direction we take as positive, which direction we take as negative, and whether it comes out to positive or negative, it will be in that direction. We'll see that more in example questions either way. So graphical representation of electric field strength versus 1 over r squared should be a straight line going through the origins, since the equation is q over 4 pi epsilon naught r squared. So what we've done here is we compare it to the equation of a straight line. We plotted y as e, x as 1 over r squared, so 1 over r squared. That means that the gradient of this line should be equal to q over 4 pi epsilon naught. So q, since all of these are constants, 4 pi and epsilon naught are constants, we could use the gradient multiplied by 4 pi epsilon naught to find the charge of the object that caused the electric field strength. So again, a reminder, when we talk about electric field strength, Q is the charge of the point charge causing the field, basically. This is a nice example question. It tells us the radius of a gold nucleus is about this much. So we have a gold nucleus. You know that in the nucleus of an atom, you only have protons that are charged and neutrons. It tells me that I have 79 protons. So, and it also tells me the radius of the nucleus. So from there to there. Then it says to estimate the electric field strength at the surface of the nucleus. Now we know that this is not a uniform electric field strength because it's a spherical object, so a nucleus is spherical. We can approximate that all the charge comes from the center of the nucleus. And I know that the electric field strength around a radial, around a point charge can be calculated using Q over 4 pi epsilon naught r squared, Q being the charge that causes the electric field strength. So it wants us to find it at the surface of the sphere. So that means I already know that the R should be I should be using the radius because it's right at the surface of the nucleus. And now, how can I figure out what Q is? What's the charge of a gold nucleus? Well, if the only part in the nucleus is the protons that are charged, we know that each proton has a plus E charge, just like an electron has minus E. We know that E is 1.6, the elementary charge, 1.6 times 10 to the minus 19 coulombs, which means I have 79 times 1.6 times 10 to the minus 19 coulombs worth of charge. So basically I took the total charge of the nucleus as the charge of the point mass over 4 pi epsilon naught times the radius, which is the distance from the center, since we're modeling a sphere to be a point charge, squared, and that should give us about 2.3 times 10 to the 21 newtons per coulomb at that point. So now going back to the learning outcomes, we have looked at Coulomb's law between 2 point charges. Very important. Don't forget that this applies only to 2 point charges because the electric field strength drops the further you go from it. So the force experienced by another charge in the field will also drop the further you move away from it, just like in gravitational fields. We looked at the electric field strength for a point charge. Remember that for uniform electric fields, it's just simply F times Q, because the force is the electric field strength is the force experienced per unit charge. Oh, sorry, that was wrong. So the electric field strength is a force per unit charge that it will experience in an electric field, in a uniform electric field. And yeah, obviously the force can be calculated using E times Q. Then we spoke about this as well. Now we're going to talk about the similarities and differences between gravitational fields for a point mass and the electric field for a point charge. Just to remind you again, when we talk about point particles or spherical objects, they both produce radial fields. So gravitational and electric fields around point masses and charges point masses and point charges produce radial fields. Their equations actually look very similar too, but in terms of gravitational fields versus electric fields, what property creates the field? Well, the property that creates the field in terms of gravitational is mass, and in terms of electric fields is charge that creates the field. What type of field is produced? Well, in terms of gravitational fields, it's always attractive. So that's the main difference, actually. Masses always attractive. Masses always attract each other. They never repel each other. In terms of gravitational fields, in terms of electric fields, though, positive point charges produce a repulsive field, meaning the direction that of field is away from the object, it will repel a positive charge. In terms of negative point charges, that produce an attractive field, the direction of field towards the object, which attracts a positive charge. So it's attractive when it has to do with negative, and repulsive when it's got to do with positive charge. Gravitational field strength. So the field strength, in terms of gravitational field strength, is the force per unit mass. In terms of electric field strength, is the force per unit positive charge. Then we also have the forces between them. So forces between masses in this case will be minus g m over r squared, whereas the force, electric force, is q over 4 pi epsilon naught r squared. So you can see here they're so similar in terms of the way they look. If we even compare the radial field strength, so for the field strength of point charges, it's minus gm over r squared, whereas for the electric radial field strength is q over 4 pi epsilon naught r squared. It depends on whether the force will be positive or negative, depending on what the charge is, if it's positive or negative. And they both have the type of field that they produce is a radial field. If it's a point charge or point mass. So you can see that the biggest difference is that gravitational fields are always attractive, whereas electric are not always attractive. And obviously that gravitational fields have to do with masses and electric fields have to do with charges. The rest is very similar, as you can see from the comparison. Yes, I hope you understood this. If you have any questions, please do ask me in class. Thank you.